All right, welcome back, folks. Hopefully you're enjoying these videos from Professor Carbon. In this video, what we're going to do is go over a synthesis problem that's really centered on getting comfortable with a lot of our electrophilic aromatic substitution reactions and putting those together and being able to manipulate various ortho or para directing groups versus meta directing groups to be able to come up with the full pattern here on this molecule. And this one's going to be a challenging synthesis because we're going to have to install 4 different groups on this benzene ring. And we're going to have to do it from benzene, which is quite grueling. And that means that we're going to have to play some switcheroos for what our ortho para directors or our meta directors are. For those of you that like these sheets, please feel free to download them in advance on the Patreon page. And also, please do take a few minutes just to put some thoughts together right now. Even if you can't get all the way through the synthesis problem, it really is important for your own learning that you just start to be able to think retrosynthetically and go backwards. Maybe start with benzene and go forwards and see where you can go. Often these problems are best solved with a little bit of forward over here and a little bit of backward over there. And maybe you can get them to get together in the middle and then go back and put all the pieces together. So please do that right now. All right, welcome back, folks. What I'm going to do is just start talking through some of these. And like I said, sometimes it's easier to go forwards, and sometimes it's easier to go backwards, and sometimes it's easier to do a little bit of both. At least when I look at this structure, you know, we've got 4 groups all over the place on this ring system, and that's going to make life difficult because we've got a little bit of 1, 2, 3, 4. And generally what I tell folks to do is label these as either being ortho-para directors or meta directors right off the bat. And so this one's going to be a meta director. Bromine, remember, is deactivating, but technically it's an ortho-para director. NH2 is our very powerful ortho-para director, but the downside with it is that we can't do Friedel-Crafts. Really either kind with a free NH2, and it's because the acid chlorides will react with the amine and you'll make amides, or it's because the aluminum trichloride Lewis acid will bind to the very basic aniline and you'll shut it down. And so usually when I have an aniline here, I make a very careful note to myself to remind myself that it's a problematic functional group. All right, this one is a really good ortho-para director, though, in methoxy. Now, the other thing that I recognize right off the bat with the methoxy is there aren't too many ways we know of to make a carbon-oxygen bond on a benzene ring directly. That's one of the more rare ones to do. And so right off the bat, there's going to have to be at least one little trick in this synthesis to complete it. Okay, one of the things I like to do when thinking about it is, and I'm just going to scroll all the way down to the bottom here so that we can chat through some of this. Redraw the structure. Bromine, chlorine, bromine. All right. So here, when thinking about this, often, we don't know a great way to put NH2 directly in place. Generally, we teach students to access that NH2 from the nitro. So I think that that's an okay thing to do going backwards, is just to think about, having the nitro there. And often that might be a problem because we might need the ortho-para switcheroo ability, because remember, nitro is a very powerful withdrawing group, and so it's a meta director. And NH2 is a very powerful activating group, and so that makes it an ortho-para director. But here, because we have the CH3 hanging out, and because that CH3 is meta to this NH2, they're activating the same spots. So if we think about the methoxy here being an ortho-para director, it's going to activate these spots. And if we think about the NH2 being an ortho-para director, it's going to activate these spots. And so those two are really reinforcing each other. And so by going from the NH2 to the nitro, this methoxy then is still the best activating group, whereas the NH2 was over here. But because those two are pointing at all the same positions, that's not such a problem, really. Then if the OCH3 is the most powerful activating group, we can go backwards and really we can remove either the bromine, or we could remove the methyl ketone. And I would probably remove the methyl ketone only because I'm aware of reactivity where if you expose methyl ketones to bromine, you might accidentally brominate the methyl a little bit. So that's usually covered in the chapter on enols. Don't worry about it here, but I might go back to this. And when thinking about this reaction in the reverse, what we want to do is think about, where is the EAS going to go? And again, this is our most powerful directing group, and so it's going to activate these three positions. And one of the things, hopefully, that you remember is it's very difficult to get EAS between two groups. And so often that ortho position that's between the methoxy and the nitro, that one's going to be more or less blocked or shielded. So I'd expect pretty good selectivity up to here, because this one position is already blocked with the bromine. Now, because retrosynthesis is really more of a thought exercise, and it never hurts to have too many pathways that you might be able to reconnect. So maybe what we want to do is just dash out this other pathway here real quick where we start with the methyl ketone. So that could be a possibility there. In either event now, what we can do is take both of these back to the same starting material. Because if we take this material with the methoxy being the really good activating group, it's going to go either here or here. And that one's going to be tough to control. So in a lot of these synthesis problems, there's almost always one step where you can't get good para versus ortho selectivity. And generally, I'm okay with that as an instructor because that's a very real problem that we encounter. And often what we'll do is subtly tweak the experimental conditions to try to make that ortho-para or para-ortho selectivity as good as we can possibly get it. It's almost always never quite perfect, though. All right, and so this is okay. Now we've got a big problem now, and that is how do we put this OCH3 and this nitro together? Because we can't just nitrate, and I'm going to do this here, an arrow over it. We can't just simply nitrate this molecule, because if we did, again, it's promoted here, and we'd probably expect the most product over there. So that would be the wrong spot. So we're going to have to do some other switcheroo. Now, we do know how to put nitro in place. And so maybe this is where we go from thinking backwards to thinking forwards and see what we can come up with. So from here, I definitely can take benzene, which is our starting materials, and we can treat that with HNO3 and H2SO4. Which are kind of our classic mixed acid conditions. And that would put a nitro in place. And that's perfect, so that's okay. And because the nitro is deactivating, we usually get really good selectivity from mononitration. So it's not an issue of getting like polynitration all the way throughout. Now the hiccup though is I don't know how to make our E plus reagent BOCH3 plus. This isn't really a reagent that I'm familiar with. And so I can't think of what that reaction would be in the forward direction. I do, however, know that maybe we can play a classic switcheroo, and really there's kind of two approaches to put that methoxy in place. One of them would be to brominate instead and use bromine as our intermediary. And so that would go meta, because the nitro is a really powerful meta-directing group. And then we could think about really two different pathways to convert that to an OCH3. One that many of you might be tempted to use is to use palladium and methoxide, so presumably sodium methoxide or some other base. The issue there is it turns out palladium with methoxide is actually a problem. You'll end up generating some formaldehyde. So experimentally, this one's slightly problematic because of that. It doesn't work anywhere near as well as sodium hydroxide does, which is a reaction covered in a lot of textbooks. So this one's good. Methoxide sometimes is a problem. The other way maybe is if we have very strong base, and so we can use methoxide NaOCH3, and maybe we can really cook this hot and get benzyne chemistry to happen. And that benzyne reaction, then sometimes you can end up with different products out because you're going through the aromatic triple bond group. So benzene. The problem there is you can end up with a mixture of regioisomers as well. So I would consider that an acceptable answer. It might not be the best answer because of the regioisomer problems going through benzene. The other way that you can do it is actually to take this instead and do a second nitration. And because now we have a very electron deficient ring, one with more than one very powerful electron withdrawing group, here we have two of the best. And nitro ends up being an okay leaving group for nucleophilic aromatic substitution. And so now what we can do is take that NaOCH3, that sodium methoxide, and cook it up and do now a nucleophilic aromatic substitution. And the reason I like this is after we put that methoxy in place, we go from having a very strong withdrawing group to a very powerful donating group. And so if a nucleophile needs to attack that pi system for our nucleophilic aromatic substitution, we're really going to slow it down by having a methoxy group on there. And so we should be able to get good selectivity for one substitution instead of two substitutions. So that's a critical part about this. And that would then complete or connect the dots up to this critical intermediate that I've already identified here. So I'm going to go up to the top now and just fill in what I would consider a reasonable answer to this problem. So we need some H2SO4 and some HNO3 for the first nitration. Now, technically, you probably could put excess of this stuff and a little bit of heat in there, and that might be acceptable to do another nitration. But often we want to be very careful with nitration, especially, and so I would probably write this as two separate steps, even though it's really the same reagents both times. But those mixed acids are both dangerous experimentally, and they're problematic because of the potential to make explosive byproducts. So get to here. Now I might do NaOCH3 for our methoxide. We might have to apply a little bit of heat to that. So that would get me to here. Now, I said before I like brominating first instead of putting the ketone in place, because I know you can accidentally brominate ketones sometimes. So just avoid it if you can. And, just on polyhydroxylated material, again, you don't even need a Lewis acid. Here, I wrote the Lewis acid because that nitro is a very powerful withdrawing group. And in the lab, we might try a number of different conditions where we just tweak the Lewis acid a little bit to see if we get it or not. Now here, I'm going to put plus ortho to OCH3 because I know that there's a byproduct where I'll probably get a little bit of bromination up here. And it'll probably be difficult to separate that out from the desired product. But it's one that eventually we're going to have to deal with doing that anyway, so might as well do it here. All right, now I'm going to do some Friedel-Crafts conditions. So we'll use some acetyl chloride, and we'll use some AlCl3. And the nice thing about both this step and this step is I'm adding a withdrawing group or a deactivating group to the ring. And so that'll help solve the problem of overfunctionalization. So as long as you start high and you kind of go downhill, you'll be able to pause there. Now we have to reduce this nitro group, and there's a lot of conditions that could do that. So palladium and hydrogen gas could do that. As a synthetic chemist, I recognize that bromine could also be reduced under those conditions. And some of our other conditions, like a Clemmensen reduction, might accidentally reduce that carbonyl. So we probably want to be a little careful with what we put in here. And I'm just going to put zinc metal, and I'm going to denote that it's zinc 0 to put it in the zinc in its elemental form to tell us that that's zinc in its metallic state. And then I'll put a little bit of HCl here. And that should be enough to reduce this down to the NH2. And of course, under the acidic conditions with HCl, it'll be the NH3 plus ammonium cation, but often we exclude these kinds of basic workups from synthetic sequences like this. So please do forgive me for oversimplifying that step. It's not that it's not needed, it's just that we often skip writing it out. Okay, so that would get us to the product, and wow, is that a bunch of steps. So if we go back all the way to the top here, we've got 1, 2, 3, 4, 5, 6 steps. So that's a pretty long synthetic sequence for us to have to go back through all the way and then talk through all the regiochemical issues. And so hopefully you feel a little bit more comfortable now with my explanation about how one could go about doing that. If you're enjoying these videos, please do follow us on YouTube. Watching this crest its first 50 followers was awesome. Watching it get a little bit higher has been even more fun. So please do keep subscribing to our YouTube channel. I very much appreciate that. Also, feel free to give us a like or a retweet on Twitter or become a patron subscriber. So thank you. Please watch the next video.